Welcome back everyone. In this particular video, I am going to illustrate to you the Leibniz Rule, the most powerful technique of integration of parameterized functions, and also known as the Feynman's technique or Feynman's trick. You can't imagine, if you don't know really what is Leibniz Rule, you can't imagine the power of it. It almost simplifies each and everything. By one way or the other, you can apply it to any parameterized functions and reduce it to whatever you like. Almost everything, not every. This video is by me, the director of mathesics.edu, and for listening to these videos more, please to subscribe my channel. But learning is important at first, so we must focus on that. Let's begin. Aim of the feature is mainly, in this particular video, we are going to understand the ways of doing this stuff, the Leibniz rule, and subsequently see certain ways to recognize how we are going to tackle this rule. Now, what is the Leibniz rule? In the next two subsequent slides, we are going to see what is really the Leibniz rule. Let there be a function small f of x which is continuous and differentiable up to first order at least. What I mean by first order? You know, I know. But if you don't know, I know. No problem. Then up to first order, I mean that if you see the second paragraph of this particular slide, then integral of capital F of x d of x is equal to small f of x plus constant of integration. Then f dash x should be equal to capital F of x. That means f dash x should be at least differentiable up to first order. And if it is differentiable up to first order, then it should be continuous. So it follows from there. Nothing new to it, but a very important and chatka aspect. Continued and finished product of the complete form of Leibniz rule. From the previous slide, we are continuing that if it so happens that this particular thing is satisfied, and similarly if we consider the definite integral u of x to v of x, integral of f of x dx is equal to small f of x, then f dash x is equal to this particular thing, capital F of v of x, v dash x minus capital F of u of x, u dash x. Now you know from the theory of composite mappings that if some mapping is being composite, means from one mapping to another there is some composition of mappings, the range of the mother function is a proper subset, or at least equal to, better to say a proper subset, but you can say equal or a subset to the domain of the function which is acting on it. Here it is capital F of x. So this is the condition that is required to be met by v of x and u of x. This is very important. Without this rule is almost proof. Most important, no one can escape it. Let us say that we have a function called capital G of x and the following equation is ascribed to it. What is the equation? That g of x is equal to the integral that we have previously seen, u of x to v of x, capital F of x dx, and from the previous result, you've also seen that earlier, but I have written it again for your convenience. We can write this down from the fundamental theorem of integral calculus. Right? Now this must also satisfy the composition mappings that I have previously told, the condition for composition. Now if you have understood it, if I differentiate the second line from the product rule of differentiation, this is precisely what I will get. This is precisely what I will get. G dash of x is equal to f dash of v of x, means small f dash of v of x, v dash x, minus small f dash of v of x, u dash x. Now what is small f dash of v of x and small f dash of v of x? Nothing but capital F of v of x. So you see the beauty of this particular rule. This rule clearly illustrates that the thing that was under the integral sign at some instant, like A prisoner in a prison, he is being freed now and he is his own king now. Means I am freeing a prisoner, but there is no sin in the country. The problem is solved. See, only a 2-line proof. But why am I teaching the proof? Some students are not interested in proofs because they want to learn the formula, they want to put the necessary functions in it and write down the answer. But why I'm teaching it is, the basic reason behind it is sometimes writing down and ascribing to the formula each and every functions becomes a messy situation. That's why it is sometimes very, helpful to think like, if I differentiate this particular function, then the function on the integral sign will come out and then it will regenerate itself, and the function which has been in the, if it is constant in the integration limits, then it's a beauty. But if it is not, then this particular thing will happen. Okay. Then it becomes a very easy situation for you to tackle if you know the proof, because proof of every formula teaches you how to proceed with that particular sum. There lies the importance. So this concludes the proof of the theorem, which is very easy. With appropriate limits, such functions like the one I have been previously telling at the first slide, that parameterized functions, here comes the parameterized functions, that capital F of x means a comma x, that is, I am differentiating, I can differentiate with respect to a as well as to x because both are independent. Both are independent. Now I am integrating with respect to x, but does it mean that I cannot integrate, I could not have integrated it with respect to a, or I couldn't have differentiated it with respect to a? There is no obvious rule regarding that. If you consider the limit of some approach to the definite integral, then also if you see, if you differentiate, if it consists of two independent parameters and you partially differentiate it, there is no one to stop you from getting another result. So you can do that in both the sides of the equation, but you have to do it on both the sides of the equation. You could differentiate with respect to a and simplify this particular integral, differentiating under the integral sign. You can do that. It's possible. And that's where some tremendously tough integrals get reduced to a very easy integrals, like integral of sine a of x minus infinity to infinity sine x by x dx. That sort of integrals gets reduced very easily. It's very easy to solve by this particular method. I must say that you must refer to Google for this particular integral of sine x by x dx, and find out the appropriate limits you can use. Right now I am not sure about the appropriate limits, but the limits, I think it's minus infinity to plus infinity, but the parent function is sine x by x, also sine ax by x, whatever you consider. If you apply differentiation under the integral sign, it becomes very easy. So there lies the beauty of this problem. I think you have liked it. There is no other way other than liking this particular video. It's very beautiful, I know. Even if you don't know, I know. So if you have not subscribed or not shared it with others who want to learn it, thanks for watching obviously, but please do subscribe and share it. And to contact me if you have any grievance or anything regarding the quality of the video or content, or you want to know something that I may discuss in in future slides that I'm going to make, please contact with me. Email is there. Thank you very much.